Yes, ma'am.
Okay, all right. In previous lecture, we have started with the first unit, that is Introduction to Reinforced Concrete, and we have completed just the introduction of what is a reinforced concrete or composite section, and what is the role of the structural designer. And then we also discussed about the basic requirements for structural design, and you also solved a small quiz based on the same. And we started about discussing the properties of various materials. In as we discussed earlier in RC, there are two major materials we have to deal with. That is, first is concrete and second is steel. We have started with the properties, and the next part we will discuss today. So in the properties of concrete, we have also discussed about the compressive strength and tensile strength, which are the major properties of concrete, how compressive strength is calculated and how the tensile strength is calculated, and how both these strength values are related with each other. As I discussed, tensile strength cannot be calculated directly by putting the concrete element in the UTM or by applying a direct tensile axial tension. We need to find out the tensile strength always in the indirect fashion, in the form of a compressive strength. Okay. Then we also started discussion on the stress strain relation. Now see, whenever we want to carry out study of any material, either it is concrete or steel or any other material, we need to focus on its stress strain behavior. See, whenever if see when you will go to the final year and when you start doing your project work, and in that project, if your aim is to study any particular material, the first thing you need to do that you have to learn its stress strain behavior, how the material behaves when it is subjected to load, and after subjecting to the load, how the deformations are obtained in the material, and based on that, what is the stress, what is the strain, and how overall the material behaves under that. So in short, whenever you want to study any particular material, you have to plot the stress strain curve for that specific material. So um, today we will focus on the stress strain relation of concrete as well as steel. So we have started with stress strain relation for concrete, and we also discussed that the curve for stress strain curve for concrete is non-linear, and it is a function of three important parameters. First is the strength of concrete and ultimate strain. Second is the duration of loading, and third is rate of loading. So I will go in detail of all. Uh, this is the curve, stress strain curve. If you observe, for different values of grades of concrete, actually these are the characteristic strength values which are written in pounds. Okay, so this is the characteristic strength of first type of a concrete or first grade of a concrete, which is around 3000 psi. Then next is 4000, 5000, 6000. So uh, I just want to discuss with you here that how the strength of a concrete has an effect on the stress strain curve of a concrete. If you consider any particular grade of a concrete, let us say the least grade of a concrete with the characteristic strength of 3000 psi, the curve is completely non-linear. If you go on increasing the grade of the concrete, the curve remains still non-linear, but it becomes sharper. Okay, so for the lower grade of concrete, hello, am I audible?
Yes, ma'am.
Okay, okay. For lower grade of concrete, the stress strain curve for concrete is flatter, and as we goes on increasing the grade of the concrete, the curve becomes sharper. Okay, so there is an effect of strength of concrete on the stress strain curve. But if you observe all these curves, the ultimate stress value, either you consider, or ultimate strain value, it is approximately same for all the four grade concrete, which is around 0.02. Or if you consider the overall spread of this curve, the strain value ranges between 0.001 to 0.003. Because if you consider the higher grade of concrete, the ultimate strain is just beyond the 0.003 value. Ultimate strain means actually the strain value at which the material fails completely. And ultimate stress is the stress, maximum stress which the material can develop within itself. Okay, so whenever we consider design of any particular structure by using any particular methodology, we have to deal with these two important parameters. What is the ultimate stress and what is the ultimate strain? Once you know these two values for any particular concrete, we can design that particular any particular section by using that particular material easily. Okay. Now, in case of concrete, the ultimate strain value is obtained around 0.002, whatever is the grade of the concrete. So, in axial compression, the ultimate strain value is considered as 0.02 for the design. Axial compression, that is when we are plotting a stress strain curve by applying a compressive load, then the value is taken as 0.002. If you are plotting a stress strain curve by applying a bending, we will get a strain in bending value, and that value normally ranges between 0.003 to 0.005, and for design purpose the value is taken as 0.035. So these two values you need to understand very carefully, and you need to keep these values in mind, because these values further we are using everywhere in the formulas. Okay, so the ultimate strain value for concrete for design purpose under axial compression is taken as 0.002, whereas the ultimate strain for concrete in bending for design purpose is taken as 0.035. Is it clear, this particular curve? Any doubt in this? Students, are you there?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Any doubts in this?
No, ma'am.
No, ma'am.
Okay. Okay. Let us move to the next parameter, which has an impact on stress strain curve of the concrete, and that is creep. Have you learned about creep?
Yes, ma'am.
Yes, ma'am.
Can you define creep? What is the meaning of creep? Even if you don't know the exact definition, you can at least try what is the meaning of, or what you understood by the word creep. Yes? Anyone from the class?
Deformation of concrete.
Huh?
Cracks during deformation of concrete.
Not exactly the cracks, but it is a deformation. Okay, so creep is defined as a plastic deformation under constant load. See, whenever we apply loading on any material, the material shows the behavior in two different ways. One is the elastic behavior and second is the plastic behavior. I hope everybody is aware of this concept, huh? Elastic and plastic behavior. Can you tell me little about elastic behavior? What do you understand by elastic behavior?
Concrete chemical moves to original position.
Pardon, please. Again. Concrete, yes.
Can take its original position. Elastic.
Can take its original position, but when?
After deformation of load.
After the
Removal of load.
removal of load, yes. When we apply a load, every material we show certain type of or certain amount of deformation, and when we remove that load, the deformation shown by the material is regained. Okay, but that is up to certain limit and depending upon a type of the material which we are dealing. For concrete, of course, it shows a elastic behavior, but very little elastic behavior, because concrete is not a ductile material, it is a brittle material. So it has certain elastic properties, but very small, very little elastic properties. So when we apply load on concrete and when we remove the load on the concrete, it will show the regain of its shape, but for a very little amount. Okay, but if we go on applying the load further, the concrete will show the plastic deformation. Okay, so this is about elastic and plastic deformation. But there is another term which is related with this deformation, that is creep. When concrete is continuously subjected to a constant load means we are absolutely not increasing the amount of load which we are putting on the concrete. Still, concrete will show certain type of deformation. See, normally what happens on a ductile material, when we apply a loading and when we go on increasing the loading, the deformation will increase. Obviously, if you remember the curve of stress strain, when we increase the strain, then only the strain will increase, right? When we increase the stress, then only the strain will increase. If you are not increasing the stress, that means if you are not increasing the load, the deformation will not be there. Whatever is the deformation, the earlier deformation shown by the material, it should remain constant. But this doesn't happen with concrete. Concrete still shows deformation even after keeping a constant stress, and that deformation is termed as creep. Okay, so this is the diagram or curve of deformation versus time. So initially we have applied certain load because of which there is a deformation. That deformation is termed as an elastic deformation. But we have kept the loading constant. Still the concrete shows a deformation. And that deformation is identified by the term creep. When we remove the load, this is the unloading point. Okay, when the load is removed, there is certainly some elastic recovery. That is, whatever is the deformation under elastic region, that will get back, that will get recovered. But there is a certain plastic recovery also. A little amount of plastic recovery will also be there, but the entire deformation will not be recovered. Means whatever the damage or the deformation shown by the material, it will not come to zero even after removal of the load. Okay, and that deformation is a permanent sort of deformation, which is normally because of the creep concept. Okay, so when we have to deal with the stress strain curve for a concrete, how this curve is obtained, that is important. How means whether we have applied a constant loading for a longer period or for a shorter period we have applied a loading which is continuously increasing in the nature. Depending upon that, the creep, this particular term comes into picture. Now, the concrete shows creep after a certain period. Means when we have applied a load and we have increased the loading till failure and we have recorded the stress and strain values, during this particular test period, there will not be creep. Creep will come into action after say 1 year or 2 years or 3 years. Okay, so structures normally be designed for 50 and 100 years. The creep effect will always be there in the action after say 1 year or 2 year or 3 year. So because of the creep, there will be always certain deformation, even though we are not increasing the load on the structure. Okay, so this is the most important parameter of creep, which takes place or which is there in action for concrete only. For steel, this concept is not there. Okay, steel does not show any creep. When we apply a loading, it will show the deformation. When we remove the loading, it will regain its shape if it is in elastic limit. If not, if it is in plastic limit, it will show the deformation. But that deformation will not increase further even if we keep the load constant. Okay, so this is a difference between two materials, concrete and steel. And the third important parameter is again the effect of rate of loading. How we are applying a load, whether it is with a constant rate or we are applying a load with a very high speed. Depending upon that also, the stress strain curve for concrete changes. You can see here in this particular diagram, this curve, if we consider this curve, which is for 1 minute, it means we have applied a load, we have increased the load just for and we reach to the failure. So the entire phenomenon of application of loading, increase in the loading and failure, everything takes place in 1 minute. Okay, in that case you can see how the stress strain curve is sharp. Now the same thing if we do in 1 hour, the curve obtained is flatter. For 1 day it is still flatter. For 100 days it is again little bit flatter. Okay, so there is an impact of rate of loading on the stress strain curve. So in the laboratory, when you have performed the compressive strain, you might have gone through the IS provisions for that test. Have you referred any IS code for the test? Students, are you there?
Yes, ma'am.
Okay. So have you referred any code during the compressive strength test? Have you performed this test, compression test on concrete? Hello? Yes? See guys, if you will not interact with me, your lecture will become boring for you also as well as for me. Okay, because I am only talking and you are, I'm not give any assurance that you are listening to my lecture or not. Okay, so try to make this particular session interactive. Otherwise, I will not understand whether you are getting the concepts or not. So let me know, have you performed the test, compression test in second year?
Yes, ma'am.
Okay. So during the test, have you referred any code?
516.
516, correct. So in that, or within the code or either in the test procedure, whatever you have written in your journal, have you read the procedure correctly? Have you observed any rate of loading for the test? Do you remember those values?
Ma'am, there was some rate fixed depending on that machine, that compressor machine.
Yes, correct, correct. But right now you must not be remembering that value.
Yes,
Okay.
ma'am.
So normally the constant rate of stress increment of 14 Newton per mm square per minute is the expected rate. Okay. And the stress strain curve plotted for that particular rate is normally considered for design criteria. Whatever the curve we obtain for by applying that particular rate, 14 Newton per mm square per minute. Okay, that rate is considered for plotting the stress strain curve, and whatever the values we obtain from that curve, that is considered for the design purpose. Okay, otherwise, if you go on increasing the rate, it has an impact on the stress strain curve, as you can see from this particular diagram. Okay, so for the design purpose, obviously we have to consider the effect of all these parameters, and then only we have to finalize one particular stress strain curve. Okay, for which normally we call it as idealized stress strain curve. So this is the idealized stress strain curve for concrete. Actually, if we consider this particular line is the actual curve. Okay, the curve has reached to the ultimate strain value of 0.002, and then the curve falls down actually. That is, the stress value starts falling down with the increase in the strain value. Okay, so the maximum strain is considered as 0.0035, at which the failure of concrete is considered. But for the design purpose, the strain value is limited to the 0.002 value. It means that when concrete reaches the strain of 0.002, it is considered that failure of material. Beyond that, whatever is the strain, whether if the stress is there, that is a strength, material has a capacity to carry the strength, little strength, higher strength, we are completely ignoring it. So the actual curve is like this. See, beyond the ultimate strain value, the stress values are started falling down. So there is no meaning of considering these additional stress and strain values. So for design purpose, the ultimate strain is considered as 0.002, and beyond that, we consider that there is a failure of material. So the curve is idealized by drawing a constant line over here. Okay, so this is the idealized curve. It is non-linear up to 0.002 value of strain, and beyond that it is horizontal. Actually, there is a failure beyond that particular point. So this is called as idealized curve. The stress corresponding to this value is called as characteristics compressive strength. Okay, and this value is denoted by FCK. I think you are aware of this notation, right? Characteristic stress. Okay, it is
Yes,
denoted by
ma'am.
FCK. Now, compressive strength, when we calculate for concrete, in India, we are actually casting a cube of 150 mm dimension, and we are curing it for 28 days, and we are putting it in compressive CTM or UTM, compression testing machine or universal testing machine, and we are finding the compressive strength by applying a axial compressive load till failure. This is the procedure, right? Now the rate of loading is kept constant. What should be that value? Everything we have discussed. What I want to notice here that we are using cube in India for finding the compressive strength. In some other countries like USA or UK or even in Europe, people are using cylinders. They are not casting cubes. They are casting cylinders having certain dimension, and they are testing those cylinders to find out the compressive strength. Now, what will happen if we are using the same material, we are using the same cement, same aggregate size, same proportion of concrete, still when we change the shape of the cylinder or test specimen, I mean to say, it has an impact on compressive strength value. The same material, if we are using for casting a cube and a cylinder, and if we are testing the compressive strength of both these specimens, we will definitely get a difference in the values. Okay, so the dimensions or the test specimen, shape and size of the test specimen both has an impact on compressive strength value of the concrete. And because of that, see, we are finding the compressive strength, we are finding the FCK value by testing the cubes. But in practice, we are not putting the concrete, or we are not pouring the concrete in cube. We are casting beams which are not having a cube shape, right? They are rectangular in cross section or sometimes square in cross section. They have a different depth and width value. The depth and width value are not exactly same. The height is not exactly same. So we are putting a concrete in a different shape, in a different dimension. So definitely there will be some impact in the strength value of the concrete which is poured in a beam or in a slab or in a column. So that change in size and shape of the specimen should also be taken into consideration when we consider the design. And for that, a multiplying factor is applied to the characteristic strength value, which is 0.67. Okay. So when we calculate the compressive strength of a concrete for a cube, the value is denoted by FCK, but the same concrete, when we put into a different material, into a different shape, into a different size, we have to apply a reducing factor of 0.67. Okay, so for design purpose, by applying this 0.67 factor, the FCK value is calculated, which is called as the maximum stress, maximum compressive stress for the member. Okay, for concrete in a member. This is for concrete in a cube. This is for concrete in a member. Now, why 0.67? Because as I have told, the height and the lateral dimension of the structural members are different than the cube dimension. Okay, and as the ratio of H by A, that is height divided by the lateral dimension, this ratio goes on increasing, the value of FCK goes on reducing. Okay, and normally that reduction becomes constant at a value of 0.67, and that's why 0.67 is a factor which is taken to find out the maximum compressive strength of a concrete in any particular member other than cube. Is it clear?
Yes,
is it clear to everybody? Okay, so this is now our idealized curve which we use for the design purpose. Okay, design purpose means for maximum. This is now the idealized curve. Now again, this maximum stress is further reduced by applying a safety factor. The safety factor is taken as 1.5 for concrete. So 0.67 FCK divided by 1.5, this value comes out to be 0.446 FCK, or sometimes in some books it is referred as 0.45 FCK. Okay, so this is called as the design value of the concrete, design strength of the concrete, and the corresponding curve is called as design curve. Okay, so this is the most important curve which is referred in the design of RC structure. This is called as idealized stress strain curve. And how from the actual curve we have moved to idealized curve for cube, idealized curve for concrete in a member, and then design curve. All these steps are well known to you now. Okay, so the limiting or the maximum or ultimate strain for concrete is taken as 0.002. The maximum value is 0.0035. For design, it is taken as 0.002. And the design characteristic, sorry, the design strength, it is not characteristic now. It is called as design compressive strength of a concrete is taken as 0.446 FCK. In other words, the value of compressive strength of concrete is limited to 0.446 FCK only. If the value of strength of concrete exceeds this value, it indicates failure of concrete in the design. Is it clear to everybody? The stress strain curve for concrete?
Yes, ma'am.
Okay. Any doubts in this? Any doubts?
No, ma'am.
Okay, okay, all right. So this is about the stress strain curve of a concrete. Let us move to the another important parameter of a concrete, that is the modulus of elasticity. Now this term you have well studied in case of steel in MOS 1, right? You have calculated the modulus of elasticity value also. By performing the tension test, you have plotted the stress strain curve and you calculated the modulus of elasticity value. So what is the value of modulus of elasticity for steel? How it is denoted?
Megapascals.
No, megapascal is it's unit. I want the value. And how it is
Sigma.
denoted?
2 into 10 raised to 5.
Yes, again?
2 into 10 raised to 5.
Correct. 2 into 10 raised to 5 megapascal is the value of modulus of elasticity, which is denoted by E, capital E. Okay, that is for steel. Now, have you learned about the modulus of elasticity of concrete? Can you tell me the value? Any single value. Like steel, you have given me the value of the steel, right? What is the value for concrete? Any
It
idea?
would be very negligible.
No. That's why we should neglect it in the design.
No.
No, we have to take into consideration what is the modulus of elasticity. But like steel, for concrete, we cannot find out the modulus of elasticity directly and very easily. This is because the stress strain curve for concrete is not a linear. It is continuously non-linear. If you are looking at this particular diagram, the curve is continuously non-linear. So we are not getting any linear portion in the curve, and because of that, we cannot find out simply what is the slope of that linear part, which will give us the modulus of elasticity value. Okay, so there are different ways of finding the modulus of elasticity for concrete. The one way is simply we draw a tangent at any particular point on the curve, and we find out the slope of that particular tangent. This is a simple method, okay, and that particular value of the modulus of elasticity is referred as tangent modulus. Okay, the tangent is drawn at any particular point. If I want to find out, say, this particular point where my arrow is pointing now, at that point, if I want to find out what is the tangent modulus, I will simply consider that point. I will draw a tangent to that point and I will find out slope of that tangent. Okay, that is the tangent modulus of the concrete or modulus of elasticity of concrete at that particular point. If I will change the point, the value will be different. Okay, so for concrete, at every point, whenever we plot a tangent modulus, whenever we calculate a tangent modulus, the E value will keep on changing. Now, for design purpose, we cannot consider this variation every time, right? We need one particular constant value. How to get that? Okay, there is another method. If we plot a tangent passing from origin, it is called as initial tangent modulus. See, this is the initial tangent modulus. We have drawn a tangent at the origin of the curve. Okay, and there is the third method in which we consider any particular point and we join that particular point with the origin. We get a straight line and we find out its slope. This is called as second modulus. Okay, for the design purpose, the value of the modulus of elasticity is always calculated based on the second modulus. So we join origin and any particular value of a point on the curve, and we find out the slope of that particular line. Okay, now when we perform the compression test on a concrete by the method, as I've told, that by applying a constant rate of loading of say 14 megapascal per minute, and we plot a stress strain curve, and when we calculate a second modulus for that curve, that particular curve or that particular value is called a short-term modulus of elasticity. Okay, and if we go on applying a load with a very less rate of loading, and when we plot a curve for that particular test conditions, and when we calculate second modulus, that value is called as long-term modulus of elasticity. Now, both these values we need to correlate with the FCK value, because according to the grade of the concrete, I am getting a different stress strain curve for concrete. Okay, from the experiment, it has been found out that the short-term modulus of elasticity of a concrete has a definite relation with the cube crushing strain, that is FCK of the concrete, and that relation is denoted by this particular formula. EC is the modulus of elasticity of concrete equal to 5000 root FCK. Now this relation we obtain when we perform a compression test by applying a rate of loading of 14 megapascal per minute on a concrete cube. Okay, and this is identified as short-term modulus of elasticity, and that value is always taken into consideration for the design purposes. Is it clear? So finding the modulus of elasticity for concrete is not an easy task. We have to take into consideration all the parameters which has a direct impact on compressive strength of concrete. We have to take care of all those parameters. We have to apply a constant rate of loading, and then we have to plot a stress strain curve, and then find out the second modulus. Okay, so modulus of elasticity of a concrete, finding the value is a tedious job, but based on the experiment, we found that this is the relation between FCK and modulus of elasticity. Okay, and this value or this formula is always considered for the design purpose. Is it clear? Modulus of elasticity concept for concrete? Guys?
Yes, ma'am.
Yes.
Yes, ma'am.
Okay. Now let us move to the next important material of RC, that is steel. And for steel, you are well aware of the tension test, then how to find out the stress versus strain curve, everything you are well aware. So I'm not going to put more time on explaining this. This is the curve for stress strain curve for a mild steel, and you can easily explain all the stages in this curve. That from O to A, there is a linear region, there is an elastic region. At point A or B, there is a yield point. It is called as yield point of the steel. Yield stress, the corresponding stress to this point is called as yield stress. Then there is a plastic region. Okay. Beyond that, there is a strain hardening. Strain hardening means the linear behavior of the steel ends over here, and there is a sudden increase in the strain even with a little increase in the stress. That is called as strain hardening. Okay, so in the strain hardening, with a very little increase in the stress, there is a very large increase in the strain. So the behavior of a steel changes here. It becomes non-linear. It reaches to the ultimate stress value corresponding to the ultimate strain value, and where the neck formation of the steel rod starts, and further increase beyond this particular point in the loading results into fracture of the steel. Okay, so this is the entire behavior of a steel under axial tension, and this is the curve for mild steel. Now, have you plotted the similar curve for HYST bar, high yield strength steel bar during your MOS 1 practicals?
TMT steel
Yes,
is it
TMT
the
steel.
same?
TMT steel, it is nothing but HYSD, high yield strength deform bars. Okay, so these are nothing but TMT steel. Now, have you obtained a similar curve for TMT steel? Yes. Have you obtained a similar curve for TMT steel? Do you remember anything? See, whatever knowledge you have obtained through MOS 1, MOS 2, everything will be required for design-based subjects. So don't forget MOS 1, MOS 2. Though you feel these subjects are difficult, still you'll require knowledge of both these subjects for learning the design of RC structure, and the next semester you have design of steel structures also. So everything will be required for learning both these subjects. So do you remember how is the curve for TMT steel? Is it exactly like this or something different?
No, ma'am, I'm
मॅम
different.
ते शार्प एजेस
It
नव्हते.
was different.
येस, शार्प एजेस नव्हते, म्हणजे ते असा शेप नव्हता असं म्हणायचं का?
Yes,
मॅम
ma'am.
अगदीच असा नव्हता, थोडा डिफरंट होता.
डिफरंट मीन्स कसा असतो शेप? थोडी आयडिया द्या मला. वॉज इट लाईक अ कॉन्क्रीट? कॉन्क्रीटचा स्ट्रेस स्ट्रेन कर्व तुम्ही पाहिलाय ना आता? तसा होता का?
नाही नाही मॅम,
मग सो डू वी गेट दिस
यासारखंच मॅम,
पर्टिक्युलर?
फक्त थोडा. हा तर
मॅम ते प्लास्टिसिटीचा रिजन नव्हता.
दिस region was not there, B to C.
येस मॅम.
And what about O to A?
मॅम लिनियर होता इनिशियली.
Ma'am, it's linear.
Okay. Now, what if you are getting a linear portion in the stress strain curve for HYSD bar or TMT bar? It means there is some recording problem. I mean, recording of loading and deformation problem, or there might be some error in the instrument itself. Okay, we never get any linear portion for the stress strain curve of high yield strength deform bars. Okay, for HYSD bar, normally we get the curve like this. Though this looks like a linear, but actually this is not linear. It is constantly non-linear. Okay, so for HYSD bar, the stress strain curve is completely non-linear, as we cannot define a yield point as clearly like mild steel. See, for mild steel, we can clearly define a yield point over here by observing this diagram. Similarly, if you observe the stress strain curve for HYSD bar, the clear yield point cannot be defined here. And that's why we make use of the proof concept. Are you aware of this proof concept? What is a proof concept? Or proof stress? Concept of proof stress. I think no, you're not aware. So, in case of HYSD bar, as we cannot define the yield point clearly, the experiments, based on experiments, it has found that when we apply a load on the steel, tensile load, and when we remove a tensile load, the steel shows regain of its shape and size. And if you go on keeping this particular exercise, it has been found that with the strain value of 0.002 or beyond 0.002 strain value, whatever the deformation developed in the steel, that is of permanent nature. It means if the strain value crosses the value of 0.002, the deformation developed in the steel is of permanent nature. And even after removal of loading, the steel will not regain its original shape back. Okay, so this particular strain value is considered as the ultimate strain here, and a line parallel to this linear portion, okay, the linear portion of the mild steel, a line parallel to this particular linear portion is plotted here at 0.002 value, and the line is extended further. The line where it cuts to the curve of stress strain of the HYSD bar, that particular point is considered as a yield point for HYSD bar. Okay, So in this particular diagram, I will go to the characteristic curve here. The line is cutting somewhere here. The corresponding stress is called as yield stress for HYSD. And this point is defined as a yield point for steel. Okay. Now, similar to concrete, for steel also, we have to define the idealized stress strain curve. Okay. The curve shown by the dotted line is actually the characteristic curve. It means whatever the curve which we obtain through experiments. To this particular values of yield stress and the ultimate strain, we apply the safety factors. Okay. For steel, the safety factor is 1.15. And by dividing this yield strain by 1.15, whatever the value of Fy we obtain, it is called as design strength for steel. Okay. And the corresponding curve is called as design curve. Now, what is happening in case of the HYSD bar, as there is no any linear portion found in the curve, we obtain a certain curved part or non-linear zone here. This is the non-linear zone. Okay. So how to find out the strength value over here or the strain value over here? See, if we consider this particular point of yield point here on the design curve, the corresponding strength is denoted by Fy divided by 1.15. If we divide 1 divided by 1 upon 1.15, that value comes out equal to 0.87. So design stress for steel is taken as 0.87 Fy for the design purpose or in the calculation. Okay. Now below this 0.87 up to the value of, say, this particular point, which is 0.8 Fy divided by 1.15, this part is a non-linear part. Okay. So up to this particular point of 0.8 Fy divided by 1.15, the curve is assumed to be linear in the HY, in case of HYSD bar also. And beyond this, there is a non-linear curve. Okay. So what is assumed? The design stress curve is linear up to the design stress of 0.8 Fy divided by 1.15, and it becomes non-linear till it reaches the value of 0.87 Fy. And the corresponding strain at this particular point is taken as 0.002 plus 0.87 Fy divided by yield E value for the steel. Okay, I think this is just the introduction session for the properties of steel, and as we move on further, you will understand what I am talking exactly. Okay, when we start actually the design process. Okay, so this is the important graph again, curve again, which is used for the design purpose of RC structures. So I just want to show you both these curves, how they are given in this particular code. I hope everybody have brought this code today. During the Monday's lecture, I inform everybody that you download this particular code from internet and keep this copy with you during the lecture. So how many from you have this particular code right now with you, either in the soft format or in the hard format? Yes, students?
On soft format.
Do you have that right now with you?
Yes, ma'am.
How many of you have it?
It's already shared on group.
Okay, so everybody on the group, you have this particular code. Quickly open this code. I'm also going to open over here simultaneously. Can you see this code on the screen?
Yes, ma'am.
Okay. Now in this code, I will quickly go to the content page. Okay. Here, section 2, all information regarding material, workmanship, inspection and testing, everything is given. If you want to recall the concepts of concrete technology, you can go through these pages. Okay, everything you can simply read it. Huh? What are the different materials used for concreting under special conditions, how the sampling is considered, and how the mixed design is carried out. The statistical quality control related criteria, the acceptance criteria, etc. In the third section, you will come to know the general design consideration. Now, everything related to beam design, basis for design is given here. What is the aim and method for design? What are the loads and forces? What is the concept of stability of a structure? How it is considered in a different way? Everything is given over here. Okay. Then as we move further, you'll find out the certain analysis part, then certain specifications for beams, for slabs, for compression members or columns, then detailing. All these specifications, keep in mind page numbers starting from 36, you will require for this particular subject of SDD1. Okay. Then special design requirements are given in section 4, which we will not require because we are not learning how to design a flat slab or how to design a ribbed slab, deep beam. This is not included in this particular subject. But staircase, yes, you will require the staircase concept. You will require footings. So again, you need to deal with the page number 63 and 66. And the most important part is section 5, structural design using limit state method. I have not yet discussed about the design philosophies, but in this particular subject of SDD1, we are dealing with one particular design philosophy, which is limit state method. Okay, so section 5 is the most important section with respect to your examination and this particular subject SDD1. Whatever the design you are going under this subject, you will be learning as per this method. Okay, so now all of you quickly open page number 67 in your code. Okay, page number 67. That is the structural design limit state method. Have you opened it?
Yes, ma'am.
Okay. Go to the next page. That is page number 69. And near the bottom of page number 69, check figure 21. It is the stress strain curve for concrete. Just now we have discussed this particular curve, right? FCK, then 0.67 FCK, then gamma M is actually the notation used to define the partial safety factor. Okay, so gamma M value for concrete is 1.5. So we get the value of design strength as 0.446 FCK. So this particular curve is there given in the code. Can you see this graph in your code, in your copy?
Yes, ma'am.
Yes, ma'am.
Okay, so you open this particular page. Now go to the next page immediately, page number 70. You'll find out figure 23. 23A is for HYSD bar or cold work deform bar. This is a stress strain curve. Just within 2-3 minutes earlier, we have discussed about this particular curve. And the next curve is for mild steel, 23B, figure 23B. It is for mild steel. Okay, these curves are given in the code because there is a certain purpose behind that. You'll be required to use these curves in the calculation part. You'll require all these values. That's why it is shown in dotted and all these vertical and horizontal lines are given in the code, because you need to find out certain values from this non-linear portion when you actually perform the design steps. Okay, so these two important curves are already given in the code. There is no need to keep in mind or mug up that particular diagram. But during the examination, the question may be asked that simply draw the idealized curve for stress strain, idealized stress strain curve for concrete, or idealized stress strain curve for HYSD bar. So in that case, you should be able to draw these diagrams and you should be able to show all the values on the diagram. Okay, so actually I will explaining you where it is given in the code. The code will be available with you during the examination. So I am actually telling you how to copy from the code. Okay, where these curves are given and from where you can copy the diagrams. Okay, is it clear?
Yes, ma'am.
Yes, ma'am.
All right, all right. Now let's come back to the presentation. It's a quiz time now. Okay, so I'm going to copy this link in your chat box. Everybody will quickly go to the chat box and solve this quiz. Have you got the link?
Yes, ma'am.